Hello guys, today me and my team presents the digital electronics TA3 activity, and for TA3 activity topic is design and implement combinational logic circuit with 4 input lines that represents a decimal digit in BCD and output is 9's complement of input number. So content of presentation is, first of all we will see what is BCD, then their truth table and K-map for outputs. Then from K-map equation we see the circuit diagram, and with the help of circuit diagram last we will see the implementation. So first of all we will see what is a BCD. So BCD, full form of BCD is binary coded decimal. BCD is another process for converting decimal numbers into their binary equivalents. It is a form of binary encoding where each digit in a decimal number is represented in the form of bits. This encoding can be done in either 4-bit or 8-bit. So we will see the example. For 0, binary coded decimal or their notation is 0000. For 1 is 0001 and for 2 is 0010.
Now, this is a truth table. So here, first we want to know what is a nines complement. The nines complement of a number is calculated by the subtracting each digit of the number by 9. For example, suppose we have a number 1423 and we want to find the nines complement of the number. So for this we subtract the each digit of the number, that is 1423 by 9. So the nines complement of the number 1423 is 9999 minus 1423, that is 8576. Now here our truth table where the decimal number are from 0 to 9. So we know how to find the BCD of the 0 to 9 number. Now 9's complement of the 0 to 9 decimal number. Here the 0 BCD number is 0000. Now 9 minus 0 is equal to 9. So 9's complement of the 0 is 1001. So likewise 1. So 9 minus 1 is 8. So 9's complement of 1 is 10000. Likewise at the ninth position, the ninth complement of the 9 is 9 minus 9 is equal to 0. So therefore ninth complement of 9 is 0000.
So now we want to construct the K-map for X. So now we observe the truth table, then we get that only 0 and 1 decimal having the 1 input respectively. So now by putting that 1 into the K-map on their respective position, so now here our don't care terms are 10, 11, 12, 13, 14, 15. Now we put the cross sign in the place of the above decimal number. By putting all these values, we get the final K-map for Y. So equation for K-map of for Y, W is equals to A complement B complement C complement. So now we want to construct K-map for X. So we observe the truth table. Then we get that 2, 3, 4, 5 decimal number having 1 input respectively. So now by putting that 1 into the K-map on their respective position. So now here our don't care terms are 10, 11, 12, 13, 14, 15. Now we will put the cross sign in the place of above decimal number. By putting all this value, we get a final K-map for X. So the equation for K-map for X is equals to B C complement plus B complement C is equals to B XOR C.
So now we have to construct the K-map for Y. So we observe the truth table. Then we get that only 2, 3, 6 and 7 number have 1 input respectively. So now by putting that 1 into the K-map on their respective position. So now here our don't care terms are 10, 11, 12, 13, 14 and 15. So we put cross sign in place of above decimal number. By putting all this value above decimal, we get a final K-map for Y. So equation for that Y, logic equation was Y equal to C. So now we will construct the K-map for Z. For constructing the K-map for Z, we observe the truth table. Then we get that 0, 2, 4, 6, 8 cells have 1 input respectively. So now by putting that 1 into the K-map on the respective position, so now here our don't care terms are 10, 11, 12, 13, 14 and 15. So we put cross sign in place of above decimal number. By putting all these value above decimal, we get a final K-map for Z equal to D complement.
At last, we get a circuit diagram, and this circuit diagram we get from the above 4 K-map equation. By using that K-map equation and by drawing the circuit diagram, now we get that here 4 input are there, that is A, B, C, D, and 4 output are there, W, X, Y, Z. Also there are the 3 gates, that is NOT gate, AND gate, and XOR gate. Here we are applying the NOT gate to the both 4 input, that is A, B, C, D, and we get A complement, B complement, C complement, and D complement. Now we want to four outputs. So for that, first we take a complement, B complement, and C complement and attach to the AND gate. So we get a first output. After that, taking the B and C and attaching to the XOR gate, we get a X output. And after that, taking C as a separate, we get a Y output, and taking the D complement, we get a Z output. Now, applying this circuit diagram onto the breadboard. So, now by implementing the logic circuit onto the breadboard, our breadboard is look like this. Here we use a 3 IC, that is NOT and an XOR. Also here we require the 4 LED and 4 resistor because 4 output are there. As we discussed earlier, by implementing the logic circuit, by using the wires and by giving the power supply, we get a 4 output and our 4 light gate blinks and our logic circuit successfully implement on the breadboard.